Welcome, welcome, welcome. You fell for it. You're taking college chem. What a fool you are. This is chapter one. We're going to be starting with a pretty short chapter, but we are going to set up two ideas that will matter throughout the entire course. What chemistry studies, see the pun I just made, and how we are going to approach problems scientifically. Uh, Unless you're some anomaly, you've already had me before. You already know the spiel. In college chem, you will be expected to do a little bit more than recognize definitions, though. You're going to need to do your job of connecting ideas, interpreting information, and working through problems even when the path is not immediately obvious. These lecture videos are meant to give you the basic framework to begin working with the material in class. Treat them as preparation rather than as something that you simply need to finish. Pause when you need to, take notes, and make a list of anything that doesn't make sense. You're probably going to be making a lot of lists. The goal is to arrive ready to use the ideas rather than hearing them from me at the first time in class. In chapter one, we're going to introduce chemistry as a discipline, the scientific approach to solving problems, and the scientific method, some practical strategies for using them and learning chemistry successfully. Oh, let's begin. Why is chemistry important? Well, thank you for asking. Uh, Chemistry matters because pretty much everything we use in every chemical process depends on understood pieces of chemistry. This slide is going to give several broad examples. You already know most of these. New materials such as stronger alloys, polymers, semiconductors, coatings, and materials designed for specific medical technological uses. Pharmaceuticals depend on an understanding of molecular structure, chemical reactions, and how substances interact with biological systems. Energy is another major area, as you all know. Chemistry is involved in batteries, which are a hot topic right now, fuels, solar cell materials, and other methods for storing energy. Speaking of storing energy, food production also requires chemistry. Shout out to all the issues we're having right now with our food supply, from fertilizers to soil chemistry to preservation and nutrition. Environmental protections requires chemistry when we identify pollutants, understand how they move through the air and water, and develop ways to remove them. The larger point is that chemistry is not isolated in our day-to-day lives. As you all know, it gives us a way to understand the composition, properties, and the changes in the material world. And that makes it useful across pretty much any field. Ooh. There are two major goals listed for this course. The first is to learn the principles of chemistry. We already have a brief understanding of that. That includes vocab, facts we need, but more importantly, it includes understanding the relationships among the ideas. How can the atomic structure affect the properties of something, and how can the quantities relate to the chemical reaction, and how do we use evidence to describe matter and change? The second goal, probably a more important goal outside of the class, if I'm going to be honest, is to become a better problem solver. That is especially important in chemistry because we know that we have to know a formula or a definition, but that's only the beginning. You have to decide what information matters, what relationships apply, and then the units that are appropriate before you can answer what makes physical sense. As we move through the course, expect some material that must simply be learned, of course, but expect even more material that takes practice. Problem solving improves by actually solving problems. There's no shortcut. Checking your reasoning and then correcting mistakes are the only way to truly learn how to problem solve. A wrong answer during practice is useful if you can identify why it's wrong, where you went wrong, and change your process that produced it. I believe in you. You can do it. Chemistry, I hardly know him. It's defined as the science that deals with the materials of the universe and changes those materials undergo. That's pretty easy, right? Chemistry is the study of stuff. That definition is intentionally broad, though. Chemistry asks what substances are made of, how are their particles arranged, and what properties they have. what happens when they interact or change. All of those are pieces you've probably been exposed to in General Chemistry 1, or if you already had me, chemistry. Chemistry is also called the central science. That does not mean that chemistry is more important than the other sciences. It just means that chemistry provides a connection among many scientific fields. Biology relies on chemical reactions occurring in cells. Medicine and pharmacology depend on molecular interactions. Geology involves the chemistry of minerals and Earth's materials. Environmental science depends on the chemical process in the air, soil, and water. Physics helps us explain the behavior of atoms and energy, while chemistry uses those ideas to understand the substances and reactions. A major theme of this course will be moving away from what we can observe on the macroscopic level, like we did in general chemistry, and what is happening at the atomic or molecular level to produce those observations. Steps in problem solving. Step 1. Read the slide. This slide introduces problem solving as the scientific process. We already know that, though. The first step is to recognize the problem and state it clearly. That often begins with an observation. If you can't recognize that you have a problem, then what are you recognizing? An observation may be qualitative, such as noticing color change, or quantitative, such as measuring temperature and mass. After that, we propose our explanations or possible solutions. In science, a proposed explanation can be tested. It's called a hypothesis. A useful hypothesis, and we'll learn that they're not always useful, should lead to an expectation that can be checked against evidence or a known. Then we decide how to evaluate the possibilities. That is where experimentation comes in. A well-designed experiment is not simply doing something and seeing what happens. It should be designed to provide evidence that helps us distinguish among possible explanations. I don't throw an apple at somebody's head and wonder what will happen. I know from previous experience being hit in the head hurts. So my hypothesis would be if I throw this apple at someone's head, it's probably going to hurt them. It was designed to provide evidence that helps us distinguish among the explanations. So these steps are useful well beyond the laboratory, well beyond chemistry in general. Chemistry problems often require the same pattern. Identify what is being asked. Organize what you know. Choose a reasonable approach, carry it out, and then evaluate whether the results make any sense. Science is both a body of knowledge and a process for building and organizing knowledge. The important feature is that scientific ideas are tied to evidence. Scientists ask questions, make observations, test explanations, compare results, and revise ideas when the evidence requires it. That means science is not a collection of statements that can never be challenged. Scientific explanations become a reliable means because they survive repeated testing and because different investigations and different investigators can examine the evidence. At the same time, new evidence can cause an explanation to be refined or completely replaced. This is why the scientific method is useful. It gives us a structured way to move from a question to evidence and then from evidence to an explanation. In actual research, which we will be looking at more this year, the process is not always a perfectly straight sequence. Scientists may return to earlier steps, modify a hypothesis, repeat an experiment, or ask a new question based on unexpected results. What matters is that conclusions are supported by evidence rather than preference or assumptions. You know what happens when you make an assumption? Bad hypothesis. So here's our steps in the scientific method. This nice little figure you'll recognize from our book from General Chemistry. There are three broad steps. We state a problem, we collect data, formulate a hypothesis, and perform experiments. And like I said, this diagram, you've seen it. It shows that the process continues beyond the single experiment. We begin with observations and questions. From those observations, we develop a hypothesis, which is a possible explanation. We then design experiments that allow us to test predictions produced by that hypothesis. If the results do not agree with the prediction, the hypothesis may need modified or rejected completely. If the results agree, the hypothesis has gained support but one successful experiment does not make it proven true. Over time, many tested ideas can contribute to a broader theory or model. Those theories can generate new predictions, which lead to new experiments. So the process continues. Laws play a different role by summarizing consistent patterns in nature. The key idea is that science is iterative. Evidence needs to feed back into our explanations, and strong scientific knowledge develops through repeated testing rather than one single major observation. Concept check, you know them, you love them. Here's a simple example of why an observation is not the same as a conclusion. In this scenario, you should read it. I'm going to pause for a second. All right. I take a balloon, I inhale, I speak, and I produce a notably higher pitched voice. From the observations, we might suspect that the balloon contained helium. However, helium is a hypothesis. The observation is consistent with helium, but it does not uniquely prove the identity of the gas. We need evidence that can distinguish from helium and other possibilities. The important college level habit is to separate what you directly observed from what you inferred. Voice became higher pitched is an observation. That gas was helium is an interpretation or a hypothesis based on that observation. One safety note, in an actual lab, we would never identify an unknown gas by inhaling it. Treat this as a thought experiment. If you have an unknown substance, it should only be tested using appropriate designs, materials. You don't know if they're hazardous or not. We don't huff gas in chemistry on purpose. Unless. Concept check. Again, based on the scenario we just talked about, which of the steps in the scientific method is missing from the following situation? Is it A, state the problem, B, make observations, C, formulate a hypothesis, or D, perform experiments? The missing step is, that's right, perform experiments. We didn't perform an experiment. We observed something and came to a conclusion. That is not the scientific method. An experiment should give us an independent evidence that either supports or contradicts the proposed identity. The textbook note gives flammability tests as an example of an additional observation that could be collected. In a real laboratory, however, any test on an unknown gas would need to be selected and performed using an obviously approved method. The larger lesson is more important than whatever helium gas or something else that we were looking at. A plausible explanation is not automatically a verified explanation. We need a test that could potentially show us our hypothesis was wrong. If every possible outcome is interpreted as supporting the hypothesis, we have not designed a meaningful test. We have created bias. This distinction will help us throughout chemistry. We frequently use observations to propose what is happening at a particle level, and then we will use evidence to decide whether the explanation is reasonable. All right, I don't want you to forget these technically four pieces of vocab that we already know, but we should make sure we hit one more time. A law says what is happening. The law is not trying to explain anything. It is just simply saying what is happening, what is observed. It's a summarization. A hypothesis is a possible explanation for an observation, which means it's tentative, we could change it, and it's testable. A hypothesis becomes useful scientifically when it leads to a prediction that can be compared with evidence. A theory or a model attempts to explain why something happens. So our hypothesis is an explanation for an observation, while our theory is an explanation for why. It's not a guess, though. A lot of the times we like to say, oh, a theory is a guess, a law is what's true. Those are way too broad of an explanation to support by a substantial body of evidence and by tested hypotheses. A model is a representation that helps us describe or predict a system. Models are sometimes just the same as a theory, but they are very useful when they simplify something that is reality, but not as easy to observe. It's important not to think of hypothesis, theory, and law as rungs on a ladder, though. A theory does not eventually turn into a law. Laws and theories answer different questions. Laws summarize patterns while theories help explain them. They are separate branches of the same tree. One branch cannot become another branch. Alrighty, and our final slide. You've already taken chemistry once, so you know this is real and this is something you need to pay attention to. And we'll go through it once, and we won't have to talk about it again, right? One of the most important steps, as you already know in chemistry, is vocab. Vocabulary matters in chemistry, matters, as it's a type of language. Terms like atoms, moles, ions, solution, and equilibrium have specific meanings, and using those words correctly help reason correctly. Some information we will need to memorize, but memorization by itself cannot carry you through this course. You also need regular practice with problem solving. Watching someone else's solve a problem can make the process look easy, but the real test is whether you can set it up and complete a similar problem on your own. Learning from mistakes is part of that process. When you miss a problem, do not only replace the answer. Identify the point where your reasoning changed direction. Was the concept wrong? Did you choose the wrong relationship? Did the units fail to cancel? Was it just an arithmetic error? Finally, ask questions. Please ask questions. Since these lectures are preparation for our work together, come to class knowing what you understand and where you're stuck. That will make our class time spent together much more useful. I cannot wait to teach you guys. For some of you, it's been 2 years since you took chemistry. For some of you, I had last year. I've missed you all, and I can't wait. See you soon.